In this video, we'll introduce the idea of parameter sharing in convolutional neural networks. So we've seen before the idea of local connectivity that convolutional neural networks leverage, and now we're ready to talk about an additional idea of parameter sharing across hidden units. All right, so this second idea that we're adding on top of local connectivity is that we will be sharing the parameters, so the weighted connections, the values of the weights of the connections between the hidden units and the units in the layer below between certain units. Specifically, what we'll do is that we'll take all of our hidden units in some given hidden layer, and we will segment the hidden units into different so-called feature maps. The units in the feature map will actually share their parameters. That is, the value of the weighted connection between a hidden unit and its receptive field input from the previous layer will be exactly the same. It will be the same values of the same connections. And now the hidden units within a same feature map, they will distinguish themselves by being connected at a different position, so a different receptive field centered at a different position in the previous layer. So specifically, normally, okay, so if we have a hidden layer with 3 feature maps, 1, 2, and 3, then say for the first feature map, all of these hidden units will be using the same matrix of connections. So for instance, this hidden unit, imagine there were 2 pixels here, then it would require a matrix 2 by 2 specifying the connection between this hidden unit and each of the pixels within the receptive field. And now say this hidden unit connected with that receptive field, which to simplify things would be just 2 by 2, would use the same matrix of weighted connections to compute its pre-activation. And similarly for that hidden unit. Also within a feature map, we'll assume that we will actually have a receptive field at each possible position within the image. There are extensions of convolutional neural networks that consider skipping certain receptive fields, but just to simplify the description, always assume we're connecting a feature map to all possible receptive fields within the image. And so when this feature map, within this feature map, when we're computing the pre-activation of all hidden units, what we'll do is we'll use the same set of parameters to compute it. And so that hidden layer would multiply this weight here by this input plus this weight here by this input plus this weight here times this input and plus this weight here times this input. And then this hidden unit here would compute this input here times this weight, this input here times this weight, this input here times this weight, and this input here times this weight. So really I want to emphasize that we're using the same matrix, the same set of parameters for this hidden unit and this hidden unit here. And now I'll say in the second feature map, it would be using a different matrix of parameters. So it would have its own 2 by 2 matrix of parameters, and then when it's computing say this hidden unit is computing its activation based on that receptive field, instead of multiplying the inputs by this matrix, it will multiply its input by that matrix instead. And then same thing for the third feature map. So I'll use the notation Wij for referring to these matrices of connection. So the matrix that connects the ith input channel in the previous layer with the jth feature map in the hidden layer will be noted as Wij. So Wij is actually a matrix here. And so this, for instance, would be W, say we have just one channel in the input, even though it's in color. Imagine it was in gray. So this would be W1, 1. This matrix here would be W1, 2. And then there'd be another matrix here, presumably, which would correspond to W1, 3. So adding parameter sharing allows us to reduce the number of parameters even more, because now the different hidden units connected at different positions actually have the same set of parameters. So we only have for each feature map to store one matrix of connections. And also it has the nice property that effectively within one feature map we'll be extracting the same feature but at every position in the input. So say feature map corresponded to a filter, if we were to visualize it, that looked something like positive weights here and then some negative weights in that region. Now it would mean that we would be extracting that feature, which is essentially detecting whether there is an edge at this particular position within the receptive field. We'll be detecting that feature everywhere in the input, because we'll be comparing that set of that filter, essentially that set of connections with that receptive field, but also the same filter with this other receptive field and every receptive field in the image. And now maybe feature map 2, so in feature map 1 we're extracting the same actual feature but everywhere, whereas feature map 2 might be extracting, say, that feature, so more like perhaps a horizontal edge, an edge going like this. And then feature map 3 could be something different, like a diagonal edge, for instance. So to describe this property that feature map 1 is extracting the same feature, it turns out we can say that the feature map, if we were to visualize it as an image, would correspond to a transformation that is equivariant. That is, if we once we've say we take this input image and we apply a transformation like a translation, well, in the visualization of the feature map, we'll actually see exactly the same transformation. The pattern of activations will be translated based on the same transformation as the one we applied in the original input. So for that reason, we'll say that the feature map will be equivariant. So putting the local connectivity and the parameter sharing ideas together, then it means that we're computing these feature maps, and these feature maps, actually the computation of these feature maps actually corresponds to computing a discrete convolution, which is a notion taken from signal processing. This asterisk symbol is the symbol for that operation. And so computing the feature maps, which are the pre-activations for the hidden layer, will correspond to doing a discrete convolution with a channel from the previous layer using a kernel matrix, which we note as Kij, where I is the index of the channel in the previous layer and J is the index of the feature map again. And that kernel is computed from the hidden weights matrix Wij. And specifically, it'll just correspond to a Wij, but where we flipped the rows and the columns in that matrix. So in the next videos, I'll talk more precisely about what we mean by discrete convolution for those that are not familiar with what it is. But just ignore that for now. It means that we're ready to look at what would happen if we were to compute the activation of a hidden layer. So specifically, I'm using here the notation from this paper by Jared et al. From NYU. And so if we call Xi the ith input channel from the previous layer, Kij is going to be this convolution kernel, which is a function of the weight matrix. And so it essentially consists in the information about the connections between the ith channel of input and the jth feature map. They'll also introduce these GJs here, which are learned scaling factors. And in their paper, they note as Yj the value of the activation at a hidden layer. And so what they considered in that paper for how they would compute the activation of hidden layer is that they would compute the pre-activations using a convolution from each of the ith input channel to the jth feature map. And then they would sum across the input channels. So we compute the pre-activations coming from each input channel, then we sum all the pre-activations. Then you apply some nonlinearity. In their paper, they chose tanh, but we could have used something else. And they also decided to introduce this GJ learned factor, which just in general for convolutional neural network is not something that's necessary, but that's something they decided to introduce. And that will correspond to Yj, which is the activation corresponding to the jth feature maps. So we will have J here will be from 1 to the number of feature maps we want to have in our hidden layer. And so each Yj is one of these feature maps, but after the nonlinearity, such as the tanh or the sigmoid nonlinearity, or any other nonlinearity we've seen in regular feed-forward neural networks. So we could have decided to introduce a bias here. So we could have added a bias, say Bj. We would have a separate bias and a unique bias shared by all units across a feature map. That's another variation. So if you look at the literature, there will be variations with respect to this particular equation, but the general idea remains the same. We're computing feature maps. And often these feature maps are, we then apply a nonlinearity on it, like a sigmoid or a tanh or a rectified linear activation function. So in the next video, I'll talk about this discrete convolution, which is going to be this procedure we'll actually invoked when we're computing the feature maps. And it's actually important because there are very efficient softwares that were written for performing this convolution very efficiently. We'll be able to leverage that when we're doing forward propagation in a convolutional neural network. And also it's important because it makes it explicit now what's the convolutional word when we're talking about why we say that these networks are convolutional.